In today's video, we're going to take a look at the motor effect, which is the idea that a current-carrying wire in the presence of a magnetic field will experience a force. And we'll cover how we can find out the direction of the force and its strength. Now, we saw in the last video on electromagnetism that a current-carrying wire will produce its own magnetic field. This means that if we place the wire between the north and south poles of two magnets, which will also have their own magnetic field, then the two magnetic fields will interact. This interaction results in a force on the wire, which will effectively push it out of the field. However, to experience the full force, the wire has to be at exactly 90 degrees to the magnetic field. Whereas if the wire is at a slight angle, it will feel slightly less force. And if the wire was running in the same direction as the field, then it would feel no force at all. To find the direction of the force, we need to know two things: the direction of the magnetic field and the direction of the current in the wire. To understand how they affect the force though, we use something called Fleming's left-hand rule, which involves taking your left hand and pointing your thumb up, your first finger forwards, and your second finger out to the side. Your first finger is meant to represent the direction of the magnetic field, so point it from the north to the south pole. Then you place your second finger in the direction of the current, and whichever way your thumb now points will be the direction of the force felt by the wire. It can be a pain to move your hand around and get it to work properly, but just practice it a few times, and remember that you can tilt your whole arm or body if that helps. Another scenario you might see the motor effect in is between the two poles of a horseshoe magnet. Between the north and south poles, we have three metal rails through which a current can flow. The two rails on the sides are fixed, but this one joining them is free to roll. As soon as we turn on the power source and the rails generate their own magnetic field, it will interact with the horseshoe magnet's field and experience a force. In order to figure out which direction the force will be in, we have to use Fleming's left-hand rule again. As the magnetic field is pointing downwards, from north to south, so will our first finger. And as the current is flowing through this rail towards us, we have to orient our second finger towards us. And hopefully, your thumb will now be pointing to the right, which is the direction of the force. The last thing we need to look at is how to calculate the strength of the force. As long as the wire is at a right angle to the magnetic field, then we can use the equation F equals BIL, which stands for force, measured in newtons, is equal to the magnetic flux density, which is just a fancy term for magnetic field strength, and is measured in teslas, times current, times the length of the wire in meters. You are given this equation in the exam though, so don't worry about remembering it. So let's imagine that we had a 10 centimeter piece of wire with a 5 amp current flowing through it, and we placed it at 90 degrees into a magnetic field that had a magnetic flux density of 0.4 teslas. What force would it experience? Well, first, we need to make sure that all of our figures are in the right units, which they are, except the length, which would have to divide by 100 to get 0.1 meters. Then all we need to do is plug all of our values into the equation. So 0.4 times 5 times 0.1, which gives us 0.2 newtons.